Okay, we are going live. Okay, so welcome to the stream. We tried to stream on Wednesday. It went poorly because I was using Wi-Fi that was spotty. We got a 100-foot Ethernet cable, so I should be solid on data. And let me see, I'm going to check the health that my software is saying. We have no drop frames. Okay, so that's the goal, is have no drop frames whatsoever. So we'll try to keep our eye on that. It seems to be doing good so far. I mean, 1080p, everything's good. So we're gonna just kind of retrace back what happened yesterday. We're gonna try to walk through all of these filters relatively quickly. So this is based off my thesis work. The link is in the description. You can go visit it. So first, we're going to talk about the PYNQ. The PYNQ is a great board if you want to do 1080p 60 frame per second video filtering. It has this really awesome video pipeline in the basic system. HDMI in, convert it to RGB with H-Sync and V-Sync, and then to the DDR and then out. And it's DVI over HDMI, not the full HDMI protocol. And here, what we're doing is we're introducing a system that has dynamic logic that allows us to take this video stream and compute on it in hardware instead of software. And this allows us to do these different filters with almost barely any latency in real time, 1080p 60 frames per second. If we use something like the ZCO104, which has the Zinc UltraScale Plus with the video codec, that we can do 4K 30 frames, 4K 60, or we should be able to do 4K 60 frames per second on that. I don't have that hardware working, so we're going to show it on this. We can do fancy configurations with dynamic partial configuration. You can go read the paper to get more about that. Today, we're focusing on the HLS. My thesis wasn't focusing on the HLS, but I used it to rapidly develop video filters. And I took a different approach to HLS. I took more of a hardware approach, where a lot of people will take kind of more of a software approach. Well, first going to show you the pass-through filter in HLS, which is going to be here. DRP, source. I'm going to look at the pass-through. You look at the H file, there's some values in there that are defined, but the most important thing here is we define the width and height. That's more important for the other things that have line buffers. But in this situation, we have the in-stream, we have 8-bit per color, 24 bits total. There's a last, which is the end of line, and 1 user bit, which is the start of frame. And then we use 65 additional user bits for some command and status transaction to the HLS. If I were to redo this, I would do AxiBus instead. So that's interesting. And these are just some helper functions, some values that just kind of get copied over from other functions. So here's our main filter operation, which all of them kind of follow the same structure. We have an input and we have an output. We have one clock, which is going to be the video operating clock, which in this situation is 142 megahertz. 1080p 60 frames is actually faster, but when you ignore the H-Sync and V-Sync and put that into when you change the video protocol to DVI, it gives you more time to process the pixels. AP control none means that there are no start, no enable, no done bit for this HLS core. It will merely operate when there is a valid input. We're using AxiStream for both our interfaces, and we are pipelining it with an initiation interval of 1. An initiation interval of 1 means that we can operate on a new pixel every clock cycle, and that every clock cycle we can output a processed pixel. And if we can hit initiation interval of 1, that means we can handle full 1080p 60 frames per second. And enable flush continues the pipeline even when we're in the back porch or in the horizontal or the vertical portion of the RGB frame. So sometimes you're not receiving data because it's just the way the monitors of the frame works in this RGB protocol. So you enable flush so that you're going to process the data that's already in the pipeline. Let's see, latencies are reported at the end, so we can look through that. So that's pass-through. In the top right, we have a pass-through going on right now, so the picture. So that's passing through the PYNQ. That is an output from my laptop, HDMI output, 1080p, 60 frames per second, and it's going to the PYNQ. Let's see if we can show you. Show you real quick. You can't really see it, but this is just the display information showing that it's 1080p, 60 frames per second. Then we just have a looping YouTube video, so you have something moving in the background. Okay. And that's pass-through, very basic. So now we're going to talk about inversion, and this is just simply almost like flipping the binary value, or in this situation taking the max value and subtracting the existing value from it. And HLS, this is very easy once you have your whole structure set up. We just take 255 minus the input value and stick it to the output. That's all we need to do. And now we can apply that filter using these two functions. And in the top right, we now have an inverted image. Okay, let's move on because I want to make sure we get through all these really quickly. So next, we have the color conversion. And a grayscale conversion, there's multiple ways to do grayscale. And in this situation, we're going to use the RGB to Y function. The Y is a different color set, color spectrum or whatever, where Y stands for the brightness. So we're going to use this function to calculate the brightness per pixel based upon the RGB values. And as you kind of already seen in the other functions, in the grayscale functions, we have this RGB function. I got this from a Xilinx white paper. There's different ways to do this, but this was an easy way to do this. And basically, we take all three RGB colors. So we have an RGB struct. We throw into this function. We get a byte out, and we assign that byte to the RGB channels. Now we're going to take those RGB channels and see what they look like in the grayscale. Hopefully, this doesn't take too long to trust this. I really, really like this IPython notebook interface. It's really helpful for developing things. So top right, we have the original image. Now we're going to load in grayscale. Booyah! Now we have a grayscale version. Man, I really like that grayscale. That's cool. So let's close out the HDMI and move on to the next one. Booyah! So next we have a threshold. Basically, we take our grayscale value, so there's a grayscale function here as well, and we say if that value is above a certain threshold, it's white. If it's below a certain threshold, it's black. So we'll go look at grayscale real quick. And same thing, we have this output value. No, we want the threshold, not grayscale. We were just at this one. So threshold. There we go. Threshold. So we're doing the grayscale value thing again, and using our little command bus, we determine the threshold value, and we change it to white or black. Let's go look at this real quick. So many filters to go through. Hope we can do this relatively quickly. Trust the kernel. Yep. trying to get to more complicated filters because that'll take more time to explain. Do our HDMI fail? Okay, HDMI is working, sweet. So now we're going to put the threshold. We have in the top right, we can change that threshold value to 40 per se. We can change that threshold value to 20. Is there 180? Yeah, we can play around with threshold values. This is useful for video, computer vision, because the threshold value, you can define it by color, find a green object, be able to make the screen only show that green object. You can do this for those type of color testing. Here we can, this is just a very basic test of changing the colors. It's another little if function, right? If red or green are at these limits, we're going to bound them. So let's go look at the bounded colors. I wish I had my little little user interface so I could rapidly be able to change up those colors. I did not have that in this situation, but we'll worry about that later. Okay, top right, original video. Oh, here we have the widget. This is what we want. So now we're going to use the widget. I love this little widget thing, right? So we have the widget. Let's take away the green. Oh, we took away the green. Let's take away the blue. All in real time, 1080p, 60 frames per second, dealing with like almost no latency whatsoever. I mean, we are going through a video buffer, so that's a little bit more latency I'm not aware of, but I gotta say, we take the red away. I really like taking the red away. I like that color a lot. So that's it, limiting the colors. Let's figure out what we have next on the lines. Yeah, very simple one. Now we're introducing an artificial. So we've been manipulating the image before. Now we're going to introduce an artificial artifact to the image. And basically it's if the X and Y values fit inside the lines, location, and size, we draw different colors. So we go to line overlay. Let that finish. Programming it way too many times. Okay, so set this up. This is just showing the time. So it takes almost no time to program these partial bit streams, which is really cool. But now we have the lines. Now we're going to use this fancy little widget. We can change out the sizes. So we can make the lines really big, right? And we can move them around. All in hardware. Very basic, but let's move on to the more interesting ones. Okay, finally got to a little bit more interesting ones. I think mirror, and then we start getting to some like really good video processing. So mirror, very basic. It's probably gonna be hard to see this one. Might have to put some words in it. So what mirror does is it saves a line, and then it plays it back later. So now we are using a line buffer. So now we have a static line buffer. So basically what happens is we're going to have a flag here. Use 0 as a flag. We have two line buffers, and basically once we reach the max, we're going to switch from one line buffer to the other for saving, and then for writing we'll switch to line buffer. So we write to line buffer 1, but we read from line buffer 0, or we write to line buffer 0 and read from line buffer 1, and we just go the opposite direction when we read, and this will give us the mirror effect. And it's okay if it's delayed in this situation because we have to wait for the delayed output. All that's going to happen is that
you'll have latency of one line, so you have an additional latency of a line of pixels, which is 1920. So 1920 clock cycles additional delay in your output. So let's see if we can even see that this mirror filter is working. I need to learn how to do little categories. Once I learn how to do categories, I'll put in categories into the videos to be like, oh, this is when we had the mirror filter. This is when we had the other filter. So let's see if we mirror this. Will you notice anything? So there's the mirror. You can kind of see the mirror changing a little bit differently. Let's see. Is there an image? Let's see if we put that display settings down. Oh, it's inverse now. There we go. Oh. Confusing. Okay, so yeah, mirror filter works great. Now let's get to embossing. Emboss filter computes the absolute difference of 2 pixels in a given direction. And so in this situation, we are doing diagonally to the top left, the difference, and then we can compute an embossed image. So let's go look at hardware embossing. Oh, and let's go look at the software for that. So our HLS, what is our HLS software for doing the embossing? So basically, we're doing the same thing with the line buffer that we did before, and we have a read and a write, and we're switching on the RGB Y value, basically if it's high or low, and then we're just getting temporary value in our read. So we save it. We save the read to the last read down here, and then we're taking last read minus current value. We get these differences, and based upon the differences, largest diff is red, or it's green, or it's blue, and then we add 128 to the largest diff, and then we threshold it. Or no, we kind of 128 is thresholding it. Or no, it's bounding it, not thresholding it, so we can have gradient. And we apply that to all the colors to get a gray image. And that's kind of, so nothing too crazy there. Okay. Embossing. So we have the image on the top right. Now we're going to do partial reconfiguration to load in an emboss filter. And now we have embossing real-time video. So let's close that out and move on to, maybe we can open up the next one. What's the next one going to be? Ooh, erode. So we're getting to some like actual video processing functions right now. So we'll let erode get the kernel started. So erosion is a fun one. Basically, you take a grid. In this situation, we're doing erosion by a 3x3 square. And we say, we erode if any neighbor is below a threshold value, then the pixel is black. That's how we do erosion. So we're only removing this situation. Basically, you have to say, are all our neighbors black? Then why do I exist? So what basically we're going to be smoothing out the edges. We're going to be removing any pixels that are kind of by themselves. Okay, so let's go ahead, let that go, close that. The video up and running again. My laptop must love it, just me taking this on and off. So now we're going to load in the erosion, and
Yeah, that is how we're eroding. The dilation is going to be really cool. So let's go look at dilation. So dilation is the opposite of erosion. So dilation looks at all the neighbors and it's like, oh, if you guys are below a threshold, I should disappear. Dilation is if any one neighbor I just found a typo in my thesis. That's a repeat sentence from the previous thing. I guess that makes sense, but that's erosion. Oh, we didn't show you the erosion. Let's go look at the erosion source before we move on. Man. Oh well. Okay, erode. We have different labels. I'm not sure how useful they are. Basically, we have a 3x3 grid, and we have a flag. Flag starts as 1. If any of the values are below a threshold value, we set the flag to 0. Only if the flag is true do we make it white. Oh, so if any neighbor is below, so this is erode if any. Okay, yeah. So it is different. If any neighbor is below the threshold value, set to black, and if any neighbor is above the threshold value, set to white. So that's the two difference. So this is white. So if any neighbor is below the threshold value, then we're going to set this to black. And we have 3 line buffers, so we can get the 3x3 area. We load these 3 line buffers into a kernel, and these are us flipping through the different line buffers. And we have a kernel, buff C. And where are we shifting? Oh, we shift right. So the kernel, so let's talk about this kernel. This is actually pretty important. So we have a window, a 3x3 window. And Xilinx provides some cool functions here in the H file to be able to shift this window. So what we do is we read in a new value, we save it to a line buffer, we shift the window, and then we need to insert 3 new values into the window to kind of load in the 3x3 window that's heading across the image. Yeah. And that's kind of that for this situation, and we have 3 different line buffers. I tried to use pointers to make this more cleaner, but to be able to achieve, again, our pipeline initiation interval of 1, I had to do this manual frame buffer shifting using a flag. And then we erode it. Okay, so dilation's the opposite. So if we go look at dilate, basically what we do any neighbor, that's immediate neighbor. That dilation function doesn't match what I think it should be. Where's the other neighbors? Shouldn't there be more neighbors than this? We're looking at just 4 neighbors. We're looking, and even then it's just 0, 0. Oh, it's because we've already erased the previous neighbors. If you think about it, we have a window that's shifting, and yeah, interesting. I haven't looked at this one in a while. But it's only checking 4, and it looks like the top left 4. It looks like it's checking itself? That's a good question. Well, let's go see what the dilation filter looks like anyways. Let's see, yes, we had no drop frames. This is great, guys. I like this Ethernet use. So now we can dilate this image. Oh. And that's about it, and we can change the threshold value. After dilation, we have Sobel edge detection. And then the kernel. And then we have our fun ASCII. Oh, and then the green screen. Have to figure out how to show that. So let's show off the Sobel. So the Sobel is we have we have a left direction and a down direction Sobel kernel. And basically we're going to do a kernel operation on a 3x3 window, and based upon the values we will be able to detect an edge in that direction, or edge perpendicular to that direction, I believe. So Sobel. The Sobel operator. So we're setting up our weights, and then we're performing our 3x3 operation, getting our values for our weights, and then we're going to add the absolute value of our weights, shifting it over based upon the bounds, and then we're going to assign a value, and then we're going to threshold the upper and lower limits to get something visible that we can see. So let's go see the Sobel filter in action. Feel free to ask any questions. Now let's see. So in the top right corner, we will have the input video is going to show up in a few seconds. Now we're going to do a Sobel operation. So this is doing a left and down Sobel, and we can change the strength of the weights, the upper limits, and the shift values to be able to kind of change how the image looks. Next, we're going to do my favorite, which is the kernel filter. So we got to close this video out though. So the Sobel is a 3x3 kernel. So the next filter is we can do custom 3x3 kernels, and based upon the weights we put into these kernels, we get different functions out of it. Doing our 3x3 matrix, our 3x3 value computations. We can do an outline kernel. I like that one. Sharpen the image. There's some other ones, right? We can blur, sharpen, emboss, outline. And these are just two examples. I feel like we should have had the other one stated. But that's okay. So we're going to go back to the kernel. Start up our video again. So input image set. Now let's apply a kernel, and now we can change it, right? So, we're gonna do an outline. Let's do a sharpen. And then we can do an emboss. And identity should just show. It's hard to tell with this image, but there's some fun images we can do to look at that. Embossing, sharpen. Some examples. So let's close this out and we can get to some of the other fun overlays. So I believe the next one is going to be our ASCII. So this allows us to put text over the screen. Oh, I gotta show you the 3x3 filter. So let's go back to the kernel, and we can actually look at what the kernel is. And it's basically like the Sobel filter, but you get to pick the weights. So in this situation, our Sobel operator, which is our thing, we now have a kernel. We have two different kernels for the X and Y. Well, we're only really doing the Y is being complete, ignoring we're operating on the single kernel right here. And that allows us to do our custom kernels. And that's how we load the kernels. These are our three different line buffers that create the 3x3 window. We do the Sobel operation, output the image, update our X and Y coordinates. And that's basically all the HLS is, to be able to do that custom 3x3 kernel. And I've expanded this up to a 14x14 kernel. It is possible, and it can operate on the image in real time. Okay, let's go look at the ASCII and hiragana text overlays. So here we have our font, all our different fonts for our ASCII characters. And basically, based upon the RGB value, instead of reading the input image, we look at our font and index into our font to be able to output text onto our screen. And we can create a string, and we can add it to the screen. Pretty straightforward. So do we have the image up in the top right? Image in the top right, sweet. Let us load in our ASCII. We have hello world in the top left, and we can change the color, the string, and the length. I don't know why it's taking so long. That seems kind of weird. Cool. Now we can load in. Let me run this again. Sometimes it takes a bit of juice. So this is an FPGA filter, and there we go. We have ASCII. And in the same vein, we also have Japanesehiragana. I like Japanese, and I found a hiragana font on GitHub, and I was like, hey, I want to try that out. So now we have a hiragana font with all our hiragana characters. And it basically does the same thing based upon XY location, string length. It reads from the font ROM and adds the color to the output image. And let us look at that. Japanese text overlay. Do image overlay. And I have to load in a green screen. Well, we can do that real quick. So let's save that. So we're going to do a Japanese font, Japanese hiragana font overlay on top of our real-time image. So we have our image up there. We're going to set up our PR, load in the PR. Now we have this dictionary so that you can be able to write hiragana in an easy way. So load that. Now we're going to load, I think, konnichiwa? Yeah. Konnichiwa. You know, konnichiwa on the top left corner. In real time. My mouse down there. Look at it. It's a YouTube video. We can open the video. We can close the video. And there we go. It says konnichiwa. And I think I have yokuso down here. Yokuso! Yokuso, a nice big text. It's a yokuso in our video. Real-time filtering. Cool. Next, we're going to do image overlay. Image overlay is kind of like a text overlay. We have a big RAM that we are saving our image in. We're using a condensed color scheme so that we can be able to fit multiple images in. So we're using a color conversion that's listed right here. So we're using a reduced color array. So 256 color array for 24-bit color values. Here's the default 20 by 20 image. Besides that, we also have an option to have an invisible color. So we have a transparent color, and we can load in different images. So let's go ahead and go to our image overlay, and we're going to put some images over our real-time video. So let's see, we got the video up there, top right corner, boom. And now we're going to load an image. And we have the BYU medallion, from where I did my thesis. Now we're going to load in a different color. It's really cool because you can slowly see us rewriting it. Now we have the BYU logo. Now we're going to load in the BYU Cougar image. I don't think we added a scale function. Did we add a scale function? Height, width. That's the location and the Y offset. Oh no, we can change the height and width according to the size. You don't have to have a perfectly square image. You can have a different size image. Here's the BYU medallion again. And there we go, we have an image overlay, and we can move its location. We can create a transparent color for like the cougar, a transparent color. And so that's it for now. In our last few minutes, we're going to look at a green screen. But first we'll need a green screen video. So let's go find a green screen video. So we're going to go to our green screen notebook. We're going to load the green screen. Then let me go hunt down a green screen video background YouTube video. Trying to find some green screen videos of like, sure, right? Okay, so we'll loop that. So what we're going to do is get the bit file streaming. We're going to take out that video, put in this green screen video, and try to match it for it. So, okay, let's go ahead and remove this video and bring in this video. We now have a green screen. Mute it. Okay, so we're now going to load in our mux that allows us to do trying to figure out. Okay, so now we have that going for ourselves. So it's doing everything, it's doing the wrong colors. So what we're going to do is now we're going to use a widget to kind of fine tune those images. And hopefully we can get something that works. We can have a dragon flying around. Okay, sweet. It's really hard to see the dragon. Okay, so now we're going to play with these values to kind of
do real-time green screen. Okay, now we're doing green screen with a dragon. I don't like that smoke. Any more green? That looks better. The smoke is there's other functions to do the green screen. So like, let me show you the green screen source. The green screen source is very basic. All we're doing is looking at the RGB value and using the RGB value to. Do I not have an H file? Okay. And so basically, we're just using the RGB value to determine which input we want to use, right? So we bound the RGB red lower upper, green upper lower, blue and lower upper, and like is it this image or is this image? And we have two input streams. We have input stream A, input stream B, and we decide which one should go to output stream A. We also have an optional output stream. This I use for utility to save one stream to HDMI and one stream to the video DMA. So yeah, I just want to do a quick presentation of all the different things, show you how simple, I guess, the HLS code is. Once you get a structure for HLS, you can be able to do things like this. We could easily increase the resolution and size and whatnot. Yeah, so we got a question here. Can you implement RISC-V on the PYNQ? So yeah, the PYNQ is a great system to implement the RISC-V. So what you could do with PYNQ is you could implement the RISC-V into Fabric, and then using this IPython notebook pages, you then could debug the processor. You could create kind of a GUI here that allows you to load software into the RISC-V, to run it, and to test it, and maybe have a virtual input and output in the Python notebook so that you could test your RISC-V. You could have a debug channel. You could try to do a GDP or something like that through this interface to be able to debug your processor. So yeah, like you can put RISC-V on any machine. There is also a Zinc processor here, so you would have to use a Zinc processor to probably communicate through the Ethernet and the UART, which is possible, but the issue is you're sharing with Linux, which is not very friendly, at least on the native PYNQ ecosystem. You don't have to run anything on the processors. You can make the buses for these peripherals available to these devices. You just need to configure it so that they can read and write to these ports, which isn't easy. If you want to do a completely custom RISC-V system, you should probably look at doing an Artix FPGA for Xilinx or a Lattice FPGA, and I'm a little hesitant using the Flash FPGAs because they have a limited program time. I would probably say Xilinx, Artix board, Lattice board. Intel Altera do have some boards. I'm not familiar with them, but you can also use those. So I think that's where we're closing. Utilization. So here's our latency, right? We have very low latency. These latencies are at 142 megahertz clock cycle. So we're dealing with super tiny latencies, super tiny utilizations of FPGA fabric. There is additional latency for the frame line buffers, but that's okay. And you can do complex pipelines, be able to apply all these filters to do crazy things. Not always the best things, but at least you can add all the filters to do lots of different setups. And that's it for this work. Feel free to look through the code, read the thesis, ask questions about HLS. HLS is kind of the future for, like, HLS has a place, it's staying, it's being used more, it provides a software approach to people who want to do hardware. It can be useful, it can be powerful, it can provide optimal solutions. I hope to be able to do future videos that address such things as Bitcoin mining on FPGAs,
RISC-V on FPGAs. I have a whole Trello board that we have ideas to work on this. I just finally got an Ethernet cable and wanted to test this out, and we got no drop frames. This worked great, so I feel more confident streaming more frequently. Thank you for showing. Please leave your comments and suggestions for future videos. Hopefully, I don't really have an editor. I plan to try doing maybe a Discord channel, having more professional editing, and some other things as we move forward. I'll probably erase the 2 other videos that dealt with this, and this video can be a main reference for those questions and interest. Let's see. For how long have we been live? 45 minutes. Okay, so I'm just going to close it off here.